You hold up your smartphone, tap the screen, and instantly freeze a moment in time. The physical world you're looking at is analog. It is a chaotic, continuous flood of light bouncing off objects in every direction. But your phone is a computer, and computers are blind to that fluid reality. They only understand the rigid language of binary numbers. To capture the scene, your camera must act as a high-speed translator. In a fraction of a second, it catches physical light, turns it into an electrical current, and translates that current into pure math. The camera's click initiates a massive, lightning-fast mathematical translation, bridging the gap between physics and computer science. The process starts when light enters the lens. The lens uses a small, adjustable opening called an aperture to control the specific volume of light allowed inside, much like the pupil of your eye. Multiple glass elements inside the lens then bend and direct those scattered light rays so they converge perfectly onto the image sensor at the back of the device. This image sensor is a grid of empty light-gathering buckets called photosites. Through the photoelectric effect, light particles hit these buckets, knocking loose electrons to create an electrical charge. Bright areas fill the buckets with electrons, while shadows barely generate any. At this stage, there is no photograph yet. The camera simply holds millions of separate, colorless, analog electrical voltages. These photosites only measure the raw volume of electrons collected, which means the sensor is naturally colorblind. Manufacturers solve this with a physical hardware layer called a Bayer filter array. As shown here, the array slides over the buckets, assigning a single red, green, or blue filter to every individual photosite. While we now have color-specific information, the electrical signals in these buckets are still analog. To a computer processor, these signals remain unreadable. To bridge this gap, the analog-to-digital converter sweeps across the sensor, measuring the electrical voltage of every bucket. It instantly assigns a specific numerical value. This dark red becomes 15, medium green is 128, and bright blue is 245. In this millisecond, the translation is complete. Physical light has been converted into digital data. Once the light is numerical, the camera's image processor, a miniature supercomputer, takes command. It immediately begins a mathematical process called demosaicing. Since each square only captured one color, the processor runs algorithms to calculate and fill in the missing colors for every space, based on the numbers nearby. The processor then begins a digital cleanup phase. Algorithms scan the grid to identify and remove electronic noise, while adjusting the white balance to ensure the colors look accurate. Modern smartphone processors take this further through computational photography. They capture multiple exposures simultaneously the moment you press the button. Artificial intelligence models analyze these combined frames to pull detail from shadows, preserve highlights, and even artificially blur the background for portraits. The camera processor mathematically reconstructs a perfected version of reality. The final output of this process is the pixel. This smallest unit of the image contains final numerical values for red, green, and blue. Millions of these specifically numbered, tiny colored squares are packed tightly together, forming the high-resolution image on your screen. This massive grid of numerical data is then compressed into a format like a JPEG and written to your device's memory. Every digital photograph is a dense, highly sophisticated mathematical mosaic. Each tap of the shutter is a microscopic relay race where physics, electronics, and AI sync to transform the physical universe into permanent digital memory.